Alright, so now on to one of the heavy hitters. We're going to go into calculus. So we have a more detailed lesson on this, or a couple lessons on this, but we're going to go over what we need to memorize here. So we're not going to be going over a lot of examples or anything. Limit definition of a derivative. So as you understand, like the power rule, product rule, quotient rule, chain rule, all of these come from this right here, but we're going to manipulate it as like a general rule to create them later. And it just makes us much faster when dealing with this. We don't have to go through the entire solution of this and working through it. But essentially what we're saying is what happens as we get close infinitely to a zero change in the function. So over an infinitely small amount of time, what is the slope, if you will? And that's what taking a derivative even means. Like we're finding the tangent line, touching at one point, one single instantaneous point of change, what have you. And you may see some question having to do with this. They're not going to ask you to take a derivative using this. That would be irrelevant because you could use other rules to just do it faster. But they may ask you about some concept that is being touched on here and make sure that you understand where these are coming from. So, the power rule. The power rule is simply that you subtract 1 from the power and multiply whatever that power used to be in front. So if we had x to the n, we multiply by n and then we reduce n by 1. The product rule is saying that if you have, and it's not always going to be like a function times a function really easily called out. You may just have to see that it's a function times a function that's being done inside of one. So that's why I put, capital F of x equals lower f of x times lower g of x. And what happens is we take f prime of x times g of x plus f of x times g prime of x. You may see it reversed around. You may see f prime of x times g of x plus g prime of x times f of x. That's just preference. Obviously, it creates the same solution in the end. The quotient rule. So instead of multiplying two functions together, it's dividing f prime of x. So take the very basic concept of a derivative, this power rule, times g of x minus f of x times g prime of x all over g of x squared. The chain rule, so this is a function within a function, and we take the derivative of the outside times the derivative of the inside. So if we're going to take the derivative of the outside, we'd obviously have to keep the inside alone. So that's where you get this f prime of g of x from. It's not just f prime x, g prime x, it's f prime of g of x. And when we do the chain rule, understand that in some ways this is basically u substitution, in that we're putting in a u for g of x and then taking a derivative with respect to u. The Riemann sum. So Riemann sums are the other half of the derivative limit definition. So this is the limit definition of integrals, taking the area under a curve. So from a to b, so those are our x values if we're talking about it that way. F of x dx meaning it was a derived function. As we approach infinity, I guess I should talk about what this actually is. So what a Riemann sum is at its core is you are taking an infinitely small shape under a curve and adding them together to create a hole. So actually I'll make a little visual representation of this. Let's get rid of this from the previous one. So if I were looking at this and I wanted to know this is an x and y, and we have this function, I want to know the area under this curve, I could take, this shape, find the area of it, and then take another one right here, another one right here, and so forth, and add all the areas together, but I would have this little bit of error. So what a Riemann sum does is it says, well, I'm going to make this shape infinitely small in width so that the error is infinitely small. So that's what it's occurring. You're still adding all these shapes together, but they're so small and so close to each other that the error becomes irrelevant. And we'll look at that. So from A to B, the limit as we approach infinite rectangles, and this is the height, so the y value times the width of the rectangle. So to take a width of something, you take the end value minus the beginning value, and then divide it by the number of items you're going to have, so n being infinite. And then we define x of I as the initial value, so we need to know how far over we're starting this integral. What's the starting value that we put right there, plus the width times what rectangle we're looking at. So if we go back to this, if we were talking about the fourth rectangle and we did the f of x, we would find the height, right, the y value. So that's what they're doing. They're saying, give me the width of the rectangle will give us, how many over we are times the number of rectangle that we're at will give us the y value here. And y times, so the height times the width gives you the area. Sum all of them together, and you have your sum under the curve. Basic integral. When you take a basic integral, this is essentially just undoing the power rule. So you do n plus 1, and then you divide by n plus 1 and you add c. So whatever the new power is, you divide by it, because obviously if you did the basic power derivative of it, you'd multiply times n plus 1 into the front, and they would cancel. So it's just undoing each other. And the plus c, the reason for this is when you take a derivative, any constant will get eliminated, and you have no idea what it is. So it becomes an unknown constant. And there are instances where you could find it given certain information, but you're not going to have to do that on the practice. Integral finding area under a curve for a defined range. So this is doing the exact same thing as a Riemann sum. And all you do is you take the integral, but you plug in that defined range. Find the area between two curves then is, you can prove this, but it's just a little trick to it. You take f of x minus g of x before you take the integral, and then you take the integral with respect to those 2 points after that. The thing to note is if you have an intersection in between these 2 points, you need to do this twice. It just won't work out. So if you had an instance like, let's see here. If I have this function and this function, Let's make a second there. And I want to know the area between them. There's this area, and there's this area. So if they asked you from point A to point B, you need to find the area between here and here first. So let's just call this point C, and add that area to the difference between B and C. There are other ways to do this, but if you try and do it all at once via the formulas that I gave you, you will come up with errors. And then we have u substitution integrals. So we can substitute u in, kind of like we did with the chain rule, to make the problem more manageable. The application is really broad for this, so I'll just work out a problem to demonstrate. You can see that right here. If I was taking the integral of x over the root of x plus 1 dx, I would substitute u in for x plus 1, and I could also solve for x then, x equals u minus 1, and plug all that in. So I eliminated all the x's, and then I phrased the root as a exponent, so by phrasing, it's in the denominator, so I can make it 1/2 to deal with the root, and I can move it to the numerator by making it negative. And then I split them because, right, they're over the same denominator, so that's fine. And multiplied everything out using exponent rules. After which I took the integral, so I raised it to that power. I raised it by 1. And then if I were to take the derivative to get back to where I was, I would have to have 2 over 3 out here. And same thing here, to get back to where I was, since I raised it up, then I would have to have a 2 out here. So if I multiply by 1/2, 1/2 times 2 would be u. And then back to this one, just to make this clear, 3/2 times 2 over 3 would be 1 as well. And that's what we needed. We need the lead integer to be 1. And then plus c. So don't forget that we have an unknown constant. And then our last step is to plug back in for u. So now that we've taken our integral, we can plug back in x plus 1 for u, and we are done. Integration by parts. So that's right here. If you're taking the integral of f of x, fg of x dx, you can use this to take that. And again, that's a little more complicated than I want to do in this video. And then you have special derivatives and integrals. I suggest you memorize these and become very fluent with them, both in this form and with the trig. I suggest you understand what they are going to look like graphically. And that should do it for Calc.